Hello, everybody. So, today we're going to talk about Euler's formula. And this, to me, is one of the most beautiful formulas in mathematics, and it's often voted so by the mathematical community. So first, recall that I squared is equal to -1, and Euler's formula tells us that the exponential function e to the I theta is equal to cosine of theta plus I sine of theta. Now, this formula is extremely important in the field of complex analysis. It comes up quite often in differential equations, but it also just has some nifty little interesting things that pop out of this formula. So we're going to focus on seeing why this formula is true and then just looking at a couple cool things you can do with it. So first of all, recall the Maclaurin series for cosine of theta and sine of theta. Cosine of theta is the series from n equals 0 to infinity of -1 to the nth power, theta to the times theta to the 2n over 2n factorial, which looks like 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, etc. Now for sine of theta, we get the sum from n equals 0 to infinity of -1 to the nth power times 0 to the 2n plus 1 over 2n plus 1 factorial, which equals theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, etc. Now, let's take a look at e to the I theta. So if we use our Maclaurin series for e to the x, but we're replacing x with I theta, this would be the series from n equals 0 to infinity of I theta to the nth power over n factorial. Now, it's a little tricky. We have to be careful in how we write this out, so we're going to do this in two steps. A couple steps, actually. So first, we take n equal to 0, and we get just 1. Then when n is 1, we get I theta over 1 factorial, which is just I theta. When n is 2, we get I squared times theta squared over 2 factorial. And then I cubed times theta cubed over 3 factorial. I to the 4th times theta to the 4th over 4 factorial, etc. Okay, now this is where it gets a little tricky, and we're going to try to break this down in a few little pieces here. So notice this I squared here, by definition, I squared equals -1. Now I cubed, on the other hand, is I squared times I, which is -1 times I to the 4th is I squared times I squared, which is -1 times -1. That's just +1. Get that written a little bit more clearly. Now I to the 5th becomes I squared times I squared times I. We already know I squared is -1 times I squared is -1. That's 1 times I. So this is just I. And at this point, we start to see a pattern. We get -1, -I, +1, +I. If we look at I to the 6th power, what are we going to get? We're going to get I squared times I squared times I squared. That's -1 times -1 times -1. That's -1. So we get -1, -I, +1, +I, -1. We'll get -I again, etc. And so we can write that in this way. E to the I theta becomes 1 plus I theta minus theta squared over 2 factorial minus I theta cubed over 3 factorial plus theta to the 4th over 4 factorial plus I theta to the 5th over 5 factorial minus theta to the 6th over 6 factorial minus I theta to the 7th over 7 factorial, etc. Now, it's a little bit messy, but what if we just take all of our even-powered terms, that's 1 minus theta squared over 2 factorial, plus theta to the 4th over 4 factorial. And we just take all those terms and we put them on one side. So we're going to group them all up together here. And then we're going to take all of our odd powered terms and we're going to group them up over here. So we get 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6 over 6 factorial, etc. But that's just cosine of theta. And here, if I factor an I out in front, what do I get left with? The rest of these terms are just the Maclaurin series for sine of theta. And that's it. E to the I theta equals cosine of theta plus I sine of theta. Okay, well that's cool, that's interesting, that's weird. Who cares? Well, let's see some cool results. First, there's Euler's identity. If we take e to the I theta equals cosine of theta plus I sine of theta, if we plug in theta equals pi, we get e to the I pi equals cosine of pi plus I sine of pi. But cosine of pi is -1 and sine of pi is 0. So this gives me e to the I pi equals -1. And if I move that over, I get e to the I pi plus 1 equals 0, which gives us a formula that relates our transcendental, our exponential e, right, and our pi, and our imaginary number I, and the identity for multiplication, and the identity for addition. Right? It gives us all of those things related together in one formula, which is pretty cool. Okay, well, what does that do for me personally? Well, maybe not a whole lot, but let's see something else cool we can do with it. Let's say you've forgotten your sum formulas for sine and cosine. Well, it turns out you can use Euler's identity to derive them very quickly. Let's take a look. Now, if I take e to the I times a plus b, so I'm replacing a plus b with, I'm replacing theta with a plus b is what I meant to say. Well, let's see how we can rewrite this a little bit. First of all, directly from the formula, if we just plug in a plus b into here, this tells me that cosine of a plus b plus I times sine of a plus b is equal to e to the I times a plus b. But I could also rewrite this using my power properties as e to the IA times e to the IB, right? If I distribute that, that's e to the IA plus IB, and my power properties for exponents splits that into e to the IA times e to the IB. And each of these can be written as cosine of A plus I sine of A times cosine of B plus I sine of B. So now if I take my left-hand side and just rewrite it here, that's cosine of A plus B plus I sine of A plus B. Now if I multiply all this out, let's see what I get. Cosine of A times cosine of B, that's just, well, cosine of A times cosine of B. Now my middle term here will be plus I sine of A times cosine of B. And my other middle term will be plus I times cosine of A times sine of B. And my last term, well, I times I is I squared, which is -1. This gives me negative sine of A times sine of B. Now, what I'm going to do is take my imaginary parts here and group them together, and group my real parts here and here together. So I'll just rewrite the left-hand side for now. That's cosine of A plus B plus I sine of A plus B, which equals cosine of A times cosine of B minus sine of A times sine of B plus, and now I'll factor the I out of my two imaginary terms, and I get left with sine of A, cosine of B, plus cosine of A times sine of B. And look, our real part here has to be equal to our real part here. Right? For a complex number, a plus ib, or x plus iy, the real part would always have to be equal if these two things are equal, and the imaginary parts would have to be equal. So we actually get both formulas at once out of this. Cosine of a plus b equals cosine of a times cosine of b minus sine of a times sine of b. And our imaginary parts will be equal, which gives me sine of a plus b equals sine of a times cosine of b plus cosine of a times sine of b. And there you have it, both of your sum formulas for sine and cosine within just a couple minutes. Now with a little practice, if you're just doing it yourself, working out the calculations and not trying to explain it to someone as you go, you can easily derive these formulas in about 2 minutes from Euler's identity. Okay, well that's cool. You got one other formula from it. Well, guess what? It works for all of these kinds of formulas. Let's do one more. We're going to use Euler's formula to prove that sine of 2 theta is equal to 2 sine of theta cosine of theta, and cosine of 2 theta is equal to cosine squared of theta minus cosine of 2 theta. Okay, so we'll write this as e to the I theta, or e to the I 2 theta. So we're just replacing what our normal theta in the formula with 2 theta, and we get cosine of 2 theta plus I sine of 2 theta. But I can rewrite this as e to the I theta squared, which is cosine of theta plus I sine of theta squared. And if I multiply this out, I get cosine squared of theta plus 2 times I times sine of theta cosine of theta. Those are my middle terms. Minus, so when I square this term, I get I squared, which is -1. So minus sine squared of theta. And this gives me cosine of 2 theta plus I sine of 2 theta equals, now I'll take my real parts and put them together, cosine squared of theta minus sine squared of theta. And I'll take my imaginary part and put it over here, and I'll put the I out in front. So this is I times 2 sine of theta cosine of theta. And once again, my real part here has to be equal to this real part, and my imaginary part here has to be equal to this imaginary part. So in conclusion, cosine of 2 theta is equal to cosine squared of theta minus sine squared of theta. And sine of 2 theta equals 2 sine of theta times cosine of theta. And that's it. Try to find the difference formulas for sine and cosine on your own using Euler's formula. Well, with that, that wraps up this video on Euler's formula, and for that matter, that wraps up this course on Calculus 2. Thank you all for watching. Have a great day.